when graphing exponential, remember back to grade 11, some of the characteristics that were in common for any of our basic exponential graphs. So something like y equals 3 to the x, regardless of what the base is, anything to the exponent 0 is 1. So the y-intercept for any of these basic exponentials is 0, 1. For our function y equals 3 to the x, if I plug in x equals 1, then 3 to the 1 is 3. So my y equals 3, and I'm given the point 1, 3. So that's going to be another point that we're going to kind of see what happens with when we transform it. If I want to look at some of the other characteristics, you'll remember that the domain is x an element of the real numbers, but y, in this case, is only values greater than 0. So you see an asymptote here at the x-axis. So y equals 0 is your asymptote for y equals 3 to the x, your horizontal asymptote. If I want to find the inverse, we know that's defined as the log function. So when I'm graphing log x to the base 3 instead of 3 to the x, all I have to do is take the x and y coordinates of the points that I know on the original and switch them. So 0, 1, the y-intercept becomes 1, 0, the x-intercept on my inverse graph, and 1, 3 becomes 3, 1. And hopefully not surprising to you is the fact that you are going to have a vertical asymptote at x equals 0 instead of a horizontal one at y equals 0. So that's what our log x to the base 3 graph looks like. We can also do transformations with this log graph. So let's say I want to vertically stretch it by a factor of 3, so the 3 is out front of the function here. That means that I want to multiply the y coordinates by 3. So if I start with 1, 0, 0 times 3 is still 0. So 1, 0 is still going to be where it was before. 3, 3 comes from the fact that I had 3, 1, and 1 times 3 gives me 3. So you can see with where x equals 3, the y coordinate has been multiplied by 3. And you can see that the vertical asymptote has not moved. It's still x equals 0 because we haven't shifted it to the left or to the right. So the only thing that's changed here is it's been vertically stretched by a factor of 3. If you want to instead change what's going on with the x coordinate, you'll remember that in the equation inside the argument itself is where the changes have to happen if it's affecting the x. And the x is a bit more complicated. Changes with the x are opposite of what we expect. So you see this 0.5 here. Remember 0.5 is like a half. The reciprocal of a half is 2. So you're going to take the x coordinates and multiply them by 2. That's what that 0.5 does inside the bracket. So for 1, 0, I'm going to take the x coordinate of 1 and multiply it by 2, which would be 2. And then this plus 2 means shift it to the left 2 units. So I'm going to subtract 2 to give me 0. So 0, 0 is a point on my transformed graph. Now I'm going to take 3, 1, and I'm going to leave the 1 alone. I'm going to take the 3 and multiply it by 2, so doubling it, I get 6, and then I want to subtract 2, so shift it 2 to the left, and I'll end up at 4, 1. And so my transformed function will look like this. And hopefully the important thing that's different with this one is that not only has it been stretched horizontally by a factor of 2, but that vertical asymptote at x equals 0 is now at x equals -2 because everything on that graph has been shifted 2 units to the left.